Last time we started looking at some of the mathematical quantities that we will require in this course, and mostly we're looking at matrices. So we'll do a quick recap of what we talked about last time, and we'll continue talking a little bit more on this. Basically what we are doing is we are preparing ourselves for a discussion of oscillations, okay, small oscillations. So as we wrote last time, matrices I will add forms now. We'll talk about them today and all that. Okay, let me do a quick recap. Let's try a color this time for recap. Okay. Okay. So last time we saw that we can decompose any n cross n matrix, any n cross n matrix into a traceless symmetric part, a part which contains the trace, which is proportional to identity, and antisymmetric part. Okay, so that's what we talked about. So let me write it. Decomposition. This you can always do. So if you have a matrix M which is n cross n, then you can do the following. You can write M as a traceless symmetric part plus trace of M, which is a number. You just add the entries which are present on the diagonal times the identity matrix, and we had to divide by 1 over n, and this n is the dimension of the matrix, plus an antisymmetric, please. Okay, this we can do. Then we also defined what are positive definite and positive semi-definite matrices. So for Hermitian case and real cases. Okay. So we also defined positive definite and positive semi-definite matrices. Let's only talk about symmetric matrices. Real symmetric. Okay, you recall that if you have a positive definite matrix, and if you take it and sandwich between any two real vectors, if that vector is non-zero, it will produce a positive number. Okay, and a positive definite matrix is semi-definite matrix is one which will produce either positive values or 0. Okay, never a negative number. Okay, that's good. So let's come back to what we want to talk today. Okay, now as you can already anticipate that because we are going to deal with symmetric matrices, that's why I'm talking about them here, we will be running into orthogonal matrices, because orthogonal, so I mean if you want to diagonalize a symmetric matrix, you do so by orthogonal transformation. So let's briefly talk about orthogonal matrices, okay, and then we'll move on to forms. So what's an orthogonal matrix? A matrix O is called orthogonal if you take the transpose of it and multiply with it, either from the right or from the left. In whatever order you do, you get identity. That's the definition of an orthogonal matrix. And there, yeah, that's fine. Okay. Which means that the inverse of O is same as the O transpose. Right? That's what this relation means. When you take O, multiply with O inverse, it should give identity. And that's what is happening here. Now I want to write down this definition of orthogonal matrix using indices. Okay. So let's say I take this piece. Yeah. O transpose is equal to identity, and I on the both sides look at the element ij. Okay. So what does it become? It becomes OIK O transpose KJ. Okay, let me be even more careful in writing this. I will write O transpose, and we are talking about KJ element of the transpose matrix, and this will be delta ij because that's what your identity matrix is. Okay, that's good. Now if I denote by, so let me denote by OI. Now see, OI is not an element of the matrix O, because any element will have two indices, ij, kl, whatever you want. So it will always have two indices like here. So clearly this is not an element of your matrix. So there is no confusion. So I am denoting by OI ith row of the matrix O. The ith row of matrix O. Okay. So you have a n cross n matrix, and it has several rows in it. So look at the ith row, and that is what I am denoting by OI. Now let's see what this relation is saying about these row vectors. Okay. So let's look at this. This becomes OI dot. Okay, I should have written this as, sorry, before I, OIK OJK equals delta IJ.